Okay, so this is a joint work with Zoltán Horváth and many other people who are not mentioned in the first slide, but this is a quite complicated framework, and many people has been worked on this topic. And our goal was to develop an accurate and fast framework, a software framework for urban air quality prediction. Our goal is to predict the concentration of pollutants in the air in a city in an arbitrary city, but we concentrated on the city of Győr in our first example because our university is located in Győr. Our main tasks can be separated. The first task is to creating a 3D geometry model. This is the geometry for the CFD. This is one of the most time-consuming part of the pre-processing phase. Then we have to build a traffic model of the city, or at least the most frequent roads of the city, in the city center mainly. We have to build an emission model to predict the amount of pollutants emitted by the cars and other vehicles. And we have to solve a CFD for the dispersion calculation. This can be also very time-consuming due to the large number of cells. And we have to validate our traffic or simulation results. And also, if we have a validated model, we can use it to analyze different traffic control scenarios, to have the policymakers to find the best scenarios if they want to choose, and they want to have a scientifically founded reason why to choose another one. And we have to build everything on this cloudy infrastructure to use many cores and supercomputers for the most time-consuming part, especially the CFD part. So this is just a sketch of the 3D air quality prediction framework. There are 4 different parts. In the first column, you can see the databases. These are fixed databases. For example, the traffic connections in the city is fixed. It won't be changed soon. This can be coming from OpenStreetMap road system, or there are some fixed meteorological simulation. The meteorological simulation is not fixed, but the points where the mesh of the meteorological geometry can be fixed. And also the city's geospatial database, it means the location of the buildings and houses and the green areas in the city and the roads are also fixed. And the pre-processing phase contains the traffic simulation, pre-processing, the CFD meshing of the computational fluid dynamics domain. And we have to make a synchronization because we have 3 different meshes, one for the traffic, one for the CFD, and one for the meteorology. So we have to find some transformations between these meshes. We have to calculate this manually in the pre-processing phase. And later then we can use automatic transformation between these different meshes. And the simulations are the traffic simulation, which can be a microscopic or macroscopic model. We can use, at this phase, we used a commercial software, Vissim and Visum. These are commercial softwares, but we are preparing a modular system, a modular framework where every part can be changed to another free or open source software version or other alternatives. And also the emission computation is by our in-house code. We use the vehicle database of the city, and the result of the traffic simulation is coupled with this well-known vehicle distribution of the city. And the 3D air quality prediction is what Johan Jansson already mentioned in his talk. In a previous phase, we used the commercial software, ANSYS Fluent, and now we are transitioning into the using free Phoenix HPC software. And if you use a commercial software like ANSYS Fluent we used before, it's very limited. We cannot use it as many cores on as many cores as we want. The license is limited, and we can use it as maximum at a certain number of cores. But if we use a free software for the CFD calculations, we can use as many as we have. And there are some measurements. The measurements are, for example, the meteorological data is measured at the mesh, and we can use it, or there are some sensors that measure the pollutants concentration in the air. This can be also incorporated into the different parts. Or in the city, we can have real-time traffic data. For example, there are certain loops and sensors which gives back the number of cars that passes through that sensor. And if we have for example, an in-house traffic simulation, maybe we can build it into our own code. So this is just the sketch of the workflow. And the pre-processing phase, as I mentioned, is about creating the CFD geometry, the 3D geometry, pre-processing of the traffic simulation, and make the synchronization phase to find the transformation between any two of them, or at least 2 and 2 of them. So the first phase is 3D CAD geometry of the city of Győr, what you can see on the picture. It was generated based on the 3D geospatial data of the city. It means that we had the sketch of the buildings in a 2D map, and also the heights of the buildings. And an automatic Blender script created this 3D mesh, so everything was pulled into 3D from 2D automatically. And in the meshing phase, there were some errors that had to be corrected manually when we meshed everything. So you can see different buildings with different colors. The coloring is based on their purpose, like industrial or for living houses and so on. Also, there are also some green areas in the city which are colored in a different color, and we can create a separate mesh for them. The traffic geometry preprocessing can be based on, for example, the OpenStreetMaps format. If you use the WISIM traffic simulation, somebody has to build this, these connections, these links and lanes and connections into the traffic simulator. And after that is built, we can fix it and run arbitrarily many times. But at the pre-processing phase, somebody has to create this traffic map of the city. Also on the first map, you can see some red lines. Those red lines are the potential points where we can have sensor data from the traffic, which can be incorporated. These are the most frequent roads of the city, and we may have traffic data later. And the synchronization is between these two meshes. So we have a 2D mesh and a 3D mesh. We have to synchronize them somehow. The input are the two geometries, and the output is with our own format. We create a link to mesh file first, and the mesh files which the first file, let me show you an example. In the background, you can see the ground level of the 3D mesh. And with white lines, you can see the traffic mesh of the city, the traffic connections of the city. And if you look closely, they are not aligned. They are shifted to each other because the coordinate systems are not aligned. So the origin of these two meshes are not coinciding. So first, we have to shift this mesh into its right position to align with all the roads. As you can see on the next picture, this is a graphical user interface we use to transform manually everything. This is in the pre-processing phase we have to do. So everything is shifted into its own place. And this transformation, this global transformation, is saved into a matrix. For every segment, we save the transformation numbers, the vector we had to shift, or also if there are some points which fall into a building, we have to move them manually. There are some unique transformations for certain points. This can be also incorporated. And the mesh file is, after we've done this synchronization, this mesh file we use is to calculating. This is also a script which calculates this file. This shows us that if you have a large segment, segment is a part of the road, and the cell of the 3D mesh, then this shows the fractions of the segments that falls into a given cell of the 3D mesh. So with this way, we can build a connection between the segments, between the 2D segments and the 3D cells. And after we get the emission values for each segment, we can use these fractions, and the separate fractions will be added as a source term to the emission file. So also there is a 3D CFD geometry and the meteorology geometry synchronization. The meteorology is given in net CDF standard file format. And it's very simple to connect these two, because here you can see also in the background the ground level of the CFD mesh. You just have to pick a point, and for that point, you can, I'm not sure if it can be seen, you have to give the latitude and longitude coordinates. So for example, you choose a well-known, the city hall of the city, and you give the latitude and longitude coordinates, and after that everything can be transformed for one mesh to another. Of course, the latitude and longitude are spherical coordinates, but we are working on such a scale that everything can be considered plane. So this is not a problem. And this is just an example of the file that we picked the point with latitude and longitude coordinates, and we mapped it into the coordinates of the 3D mesh. And also there are some other sections are calculated of that netCDF file, which parts of the whole meteorology geometry is needed for us, because only of a small part of the whole map covers the city we are considering. So in the traffic module, you have to build some data of the traffic, some initial data, which you model. It can be based on a historical traffic count data when people counted the traffic of the roads, or it can be used the monitored data of the sensors, which can be also incorporated. And at this phase, we have the VISIM and VISUM for microscopic or macroscopic simulation, or just simply use some statistical or measurement data if you want to use an in-house code. And The input and output of the traffic modules are very simple. For each segment, we have to get for each vehicle class, for simple cars, for heavy goods vehicles or buses, the density, the volume, and the average speed of those cars. And also, of course, the coordinates of the given segments. So it can be seen on this example file. There are blocks of 3 numbers. These are the densities on the given segment. There is also a segment identifier, which are the coordinates of the segment, basically. And there is also a time point, which gives us the simulation time of the line. And this is the output of the VISIM. This is its standard format. And we use these numbers, these density and velocity numbers, to calculate the emissions. The emission is based on a European standard, the Coppert model. If we know the vehicle distribution of year, we can get an emission file. This emission file gives us back, for every cell of the 3D CFD mesh, the emission of nitrogen oxide, in this case NOx, measured in microgram per second. So these numbers are in microgram per second, and these are the emission for every cell ID and every time step. This is just a part of a very large matrix. So this is our emission file. This will be the time-dependent source term for our dispersion calculation. So if we go on to the dispersion calculation, the source terms will be coming from the emission. The boundary terms at the boundaries, the large boundaries, will be coming from the meteorological data, because at the outside of the city, the buildings won't really affect the velocities and the pressures. So we use the Hungarian Meteorological Service weather prediction model, those net CDF files, and we use some interpolation for the points, or just a simple, very simple interpolation to have a boundary condition. And the dispersion module, in a previous phase, was the ANSYS Fluent that solved these dispersion calculations. It used the Reynolds averaged Navier-Stokes, the RANS. And now we are trying to transition into using some open source or free softwares, like the Phoenix HPC. So as we have heard from the previous talk, that the Phoenix HPC can be better than the Fluent in certain conditions. We hope that it can improve our results. It can run much faster. We can solve either a Reynolds average, Navier-Stokes, or some larger simulations or something like that that works best. Because if you, okay, so this is just the input and output. Because if you look at these pictures, these are just some previous results with ANSYS Fluent. These pictures were generated, and these results were validated with given air quality sensors data, and the validation was quite good. So if we can improve the CFD dispersion results, if we change the Fluent to Phoenix HPC, we hope everything will be at least as good as now. And it can be much better, because just to summarize the work in progress and future work, we can use or try to use free softwares in each part. Like for a traffic simulation, we can try something else. For the dispersion module, we are now trying to use Phoenix HPC. And if you use Phoenix HPC, as we have seen, you can try to use adaptive mesh control, because our current mesh is refined in the city center because the traffic is larger there, and it's more important to use more finer mesh there. But if you use an adaptive mesh refinement, the software will try to find out on its own where it needs to refine the mesh based on the simulation in real time. So these are the plans for the future work, and this is what we are working on. And thank you for your attention.